Okay, moving on from last time, today we are going to talk about vertical and horizontal asymptotes of a graph. Back from Algebra 2, we learned about vertical asymptotes and removable discontinuity, so we'll go ahead and start off with a recap of those two then. So a vertical asymptote occurs at x equals to c if f of c yields an a over 0 as a result then, where a is going to be any real number with the exception of 0. Removable discontinuity occurs at x equals to c if f of c yields 0 over 0, which is going to be also considered undefined, but it's a little bit more specific case. The one thing that I want to add on to these two items would be something called an end behavior, or to be a little bit more specific, a horizontal asymptote. And that is basically looking at what happens to the graph as x gets bigger and bigger, going towards positive infinity or negative infinity. So to be a little bit more specific, we're looking at the following. This notation you're going to see a lot of when you hit calculus. This says limits as x approaches towards negative or positive infinity for the function f of x is equal to some constant. So as we were saying earlier, we're looking at what happens to the graph as x gets bigger and bigger in the positive direction and a negative direction if it approached towards some finite number then. And that would then give us something called the end behavior. Now, in most cases, we call the end behavior a horizontal asymptote, and I don't actually like the term horizontal asymptote, mainly because when you think of the word asymptote, it is basically a line that the graph never actually touches. But in this case, you can see that sometimes this horizontal asymptote, the graph actually crosses over. So later on, hopefully I can give you some examples of that. So here is an example of one problem where you have all of those characteristics happening. So here I want to graph the following equation. Y is equal to 25 minus x squared times x minus 1, all divided by 1 minus x squared times x minus 5. So the first thing I'm going to do is go ahead and factor it as much as possible, so then that way I can simplify as much as possible too. So using the difference of square, I can factor the 25 minus x squared into the following, and the 1 minus x squared, I can factor that into the following as well. But you'll notice that you have these two other terms, x minus 1 and x minus 5. Now, you have 1 minus x over here and 5 minus x over here. So technically, they can cancel each other out, but I would have to reverse the order. So what I did was I did go ahead and reverse those orders, changing the x minus 1 to 1 minus x. But as a result, I have to extract a negative 1. And similarly, in the denominator, the x minus 5, I can write that as 5 minus x, so I can cancel out with the 5 minus x that's on top. But I need to extract out a negative 1 also as well. Finally, once we have everything in factored form, we're going to go ahead and cancel out all the like terms, and that now gives us the following equation. Y is equal to 5 plus x all over 1 plus x. And you'll note that I actually wrote it a little bit different using y is equal to over here, and then y is going to be, and there's like a little arrow right here, this equation right here. These two equations, graphically, they are actually going to be kind of the same thing, but not really, and it's all because of domain restrictions. And what I mean by the following is the following. If I were to try to graph it out, for the most part, these two graphs would look exactly identical. But the only difference is over here, you'll notice that I can't have x is equal to 1, nor can I have x is equal to 5. So at those 2 points, we're going to actually have something that's undefined. And since we started off with the original equation, then with that setup, with those factors, the end result is not going to have those factors. I can't technically say that these two equations are going to be exactly the same thing. But nonetheless, for the sake of graphing, we still have to simplify to this equation, so we're going to go ahead and use that then. So just keep in mind, for the sake of domain range, we actually have to consider this as our original equation. But for graphing, we're going to have to look at this equation. Nonetheless, we'll go ahead and go through our characteristics as we did back in Algebra 2. First, we're going to look at where the graph is going to be undefined, having a removable discontinuity. Now, if you remember from earlier, we said that the removable discontinuity occurs at x equals to c if f of c yields 0 over 0. So that means that if I have a factor that gets canceled out from both top and bottom, that's where we're going to have a removable discontinuity. So for example, over here, 5 minus x and 5 minus x. So at x equals to 5, because that's what gives you 0 over here and 0 over here, you're going to have an open circle then, and that's what removable discontinuity means. To be a little bit more specific as well, I want to find out what's the coordinate of the removable discontinuity. So I'm going to take 5 and plug it into the simplified equation, and that will now give me 5 comma 5 over 3. So on the graph, what will happen is at that coordinate, you're going to have an open circle then. And similarly, at x equals to 1, you're also going to have a removable discontinuity because here we have 1 minus x divided by 1 minus x, and that right there is the same factor. When you plug in x equals to 1, that gives you 0 over 0. And same as what we did over here earlier, I'm going to go ahead and plug 1 into the equation to figure out what is the removable discontinuity's entire coordinate. So plugging in 1, we get 6 on the top, and then we get 2 on the bottom. So 6 divided by 2, which is going to be equal to 3. So that is our second removable discontinuity then. Vertical asymptote is when defined at when you plug in x equals to c, you're going to get a over 0 as a result, meaning that you're only going to get a 0 in the denominator, but the numerator is going to be some other numerical value. So what that means is looking at my simplified equation, you'll notice that at x equals to -1, you're going to get 0 in the denominator. Whereas if you plug -1 on the top right there, you're going to get 4. So 4 over 0, that's your vertical asymptote then as a result. Okay. Finally, the new thing that we need to consider now is the horizontal asymptote, or more specifically, the end behavior. And I really should change this so that it says end behavior because, again, I just try not to use that term, horizontal asymptote, if possible. So the way we're going to solve for this one is we're going to take our simplified equation, and I want to look at what happens as x approaches towards positive or negative infinity. The best way to do that is I can take my equation and divide by 1 over x. Now, if you're wondering where that 1 over x is coming from, it's because what I would like to do is I need to divide both top and bottom by the biggest monomial in this case. And you'll see what will happen when you actually do that in just a little bit. So here you'll notice that the biggest monomial is going to be x, so I'm going to divide everything by 1 over x as a result. If we do so, you will now get 5 over x as the first one, and then x over x, which is 1 on the second part. Whereas the denominator, you get 1 over x over here, and then you have x over x is equal to 1. Now here, as x approaches towards infinity, it'll be a little bit more clear as to what actually happens. 5 divided by any really, really large number, like say infinity, that's going to yield 0 as a result. So that is going to go to 0. 1, nothing happens because there's no x involved, so that's still going to be equal to 1. And the denominator, when you have 1 over x, as x gets to a really, really large positive or negative number, that also yields 0. And again, for the one that's over here, that nothing happens to that one, so you're also going to get 1. So because you have 0 plus 1 over 0 plus 1, that gives you 1 as an answer. So what that means as the graph of y is going to get bigger and bigger as x get bigger and bigger, then your end result is that the graph is getting closer and closer to y is equal to 1, and that's going to be our end behavior. Now, taking everything that we just said and trying to graph it out, here's what everything looks like so far. We have our removable discontinuity at 5 comma 5/3, as we said over here. So I'm just going to draw that out. That's going to be our open circle. Then we have at x equals to 1 comma 3, and that's going to be another open circle because it's a removable discontinuity. We have a vertical asymptote at x equals to -1. So you can see here we have a dotted line that's vertical over here. And our end behavior, the I guess we can call it quote unquote horizontal asymptote, we have another dotted line that's going across like this right here. So this line y is equal to 1 is basically the result of this horizontal asymptote or this end behavior. Whereas the vertical asymptote, again, is going to be this guy over here. If you take a look at what we have graphically so far, according to what we figured out, I think we can get an idea as to what the graph actually looks like. Taking those points and kind of connecting them, and I can go ahead and maybe draw it for you guys right now. This is what it's going to look like then, the graphic for the graph. So you'll have something that is going to go down this way, and it's going to connect over here, first getting to your first removable discontinuity. Then we're going to continue on to hit the second removable discontinuity. And as x gets bigger and bigger, it's now going to get closer and closer to this horizontal line over here. That's going to be our end behavior. Thinking back also now to your Algebra 2 class, anytime you have a vertical asymptote, it is most likely what will happen is that you'll go up in one direction and then you'll appear on the bottom from the other direction. So for values of x that is less than -1, close to -1, you're going to probably start down here, and it's going to go up and up and up and up. And remember, you have an end behavior at y is equal to 1. So what that means is as x goes to -infinity, you're going to get closer and closer, not to the x-axis, but you're going to cross it over and get closer and closer to that line. So the result is that your graph will look something like this. And you probably have to excuse my graph because, this isn't exactly the nicest looking graph. Okay. Now, for those of you guys that are kind of like, you want to be very, very specific, I guess we can find out the y-intercept and the x-intercept by plugging in x and y value into the equation. But you can probably see what's going to happen over here. That's an easy answer we can solve for. For the y-intercept, we're going to go ahead and let x equals 0. So that's going to give us 0, 5 over here. And for over here, if I'm trying to solve for the x-intercept, I'm going to go ahead and set y is equal to 0 in this equation. And that's really just looking at the numerator, setting that equal to 0. So if I set this equal to 0, that's going to give me x is equal to -5. And sorry, my pen is actually kind of running out of ink because this thing is probably 16 years old. But nonetheless, here x is equal to -5. And so that means that this coordinate is going to be -5, 0 then. Okay, so that's going to be our graph. Now, let's go ahead and advance a little bit so then that way we can use kind of like a theorem to make this a little bit easier for ourselves. So suppose that your graph is, suppose that your equation is in the form of the following, where y is equal to some polynomial on the numerator on the top, divided by some polynomial in the denominator on the bottom. So a times x to the n plus a whole bunch of other terms, divided by b times x to the m plus a whole bunch of other terms. I want to look at what happens specifically when you have exponents that are comparable. To be a little bit more specific, let's look at 3 cases. If n is less than m, so that means that the numerator's polynomial is going to be smaller than the denominator's polynomial. So here's an example of that. Y is equal to 4 times x to the third plus 2x minus 1 divided by 7x to the ninth minus 4x plus 3. You don't have to worry about factoring any of this stuff because all I care about is what happens as x gets bigger and bigger in the positive and negative direction. So idea here is I want to find out what kind of end behavior will this have if there is any. So first we're going to go ahead and start by writing limit as x approaches towards positive or negative infinity. And just like we said before, I'm going to now take this rational function and divide both top and bottom by the largest monomial because remember, that's what we did over here. So in this case, I'm going to divide both top and bottom by x to the ninth. And if we do so, this is what we're going to get as a result. And you'll notice that you've basically created a whole bunch of single terms where you have a fraction within a fraction. And that's exactly what we want, even though it looks kind of nasty. The reason why we want to get that is, well, as x approaches towards infinity, those terms in the denominators are going to get so big that if you look at it as a whole for each monomial, those are going to go to 0 as a result. So for example, over here, 4 divided by x to the 6th as x gets bigger and bigger, yeah, that definitely does going to go to 0. This guy, that's also going to go to 0. This guy is also going to go to 0. The only term that's not going to 0 is this first term over here in the denominator, where you have 7 times x to the ninth, because when you divide that by x to the ninth, you're going to get 7 as a result. So the end result here is that every single term, with the exception of this one, is going to go to 0. And so that tells me that this simplifies now to be equal to 0. So in the case of if the numerator has a smaller polynomial size than the denominator, then your end behavior is going to be the line y is equal to 0, or the x-axis. And that's something that we've always been seeing so far. But now what happens if you have maybe, like, say, n is equal to m, where the polynomial for the numerator and the denominator, the size of it, the rank of it, is going to be the same thing. So once again, here's another example of that, where you have 5x squared plus something, and then divide by 4x squared plus something on the bottom. Again, we're going to go ahead and divide both top and bottom by x squared, because that's the largest monomial. And you're going to introduce now a bunch of terms with fractions in there, and you're going to have a few terms that are not going to have fractions in there. Any term that has a fraction where x is in the denominator, we know that those are going to go to 0 because of what we did previously. So that now tells us that we have 5 plus 0 divided by 4 plus 0, which is equal to 5 over 4. So that, in this problem, our end behavior is the line y is equal to 5 over 4. If you just compare that to my original equation, we can now generalize that if n is equal to m, if your polynomial is the same size as it is from the top as it is from the bottom, your end behavior is really just going to be a y is equal to the ratio of the coefficients a over b. So that's exactly what happens over here, because those are my leading coefficients over here then. Finally, for this last one, what if the numerator has a polynomial that is going to be bigger on the top and smaller in the bottom? So again, here's your example. And we're going to go ahead and start by writing the limit first. And then we're going to also divide everything by the largest monomial, which is x to the third. If we do so, this time, we're going to, again, just like before, get a bunch of terms where you're going to get 0 as a result. But you'll notice that one part that's a little bit different is that the term that does not give you 0 is actually in the numerator. So here you're going to have 4 minus 0 divided by 0 plus 0, because you see these guys right here, they're going to go to 0 when x gets bigger and bigger. And whenever you have a number over 0, then that means it's going to be undefined. So in this case, if the numerator is bigger than the bottom denominator as a polynomial, then that means that there's no end behavior here. That means that y is just going to get bigger and bigger in the positive direction or in the negative direction then. There's basically no horizontal line that the graph is going to get closer and closer to. All right, that's the end of it. Have a good day.